Okay, good morning. Welcome to the beginning of week 9. We've got confidence intervals in the rearview mirror, hypothesis test down the road. If the course, every course I teach in elementary statistics, it tends to come off the rails a little bit at the same place. You can pinpoint it. And it's right at the introduction of the central limit theorem. And it's because the concepts thereafter are, they're complicated. They're very difficult to get first time through. Now, having said that, there's still 36 of you between the two classes. We started with 66, so you can start the day by patting yourself on the back, saying, yes, I'm a survivor, I'm like a cockroach, you can't kick me out of this class. And that'd be a good attitude to have. You got to keep running right now. 30 out of 36 of you are over 400 points, which is just great. I think 20% of you are at 600 points, which is just super. If you're not in those categories, just keep grinding. Just keep grinding for the next 3 or 4 weeks, and you're going to find yourself, or not, you're going to find yourself, I think, within reach of that 700-point goal. And if you're not, you can kind of decide to withdraw at that point. But I would say just keep grinding over these next couple of weeks and build that point total up. Last week was confidence intervals, tough concept. A lot of you expressed having difficulties getting it down. I think I'm going to throw out that discussion that we had on confidence intervals that absolutely proved that many of you had difficulty with the concept. I know I gave you 3 different questions from which to choose, but they were all really aimed at the same thing. Okay, they were all aimed at explaining to me, explaining to yourself how the machinations which lead to creating a confidence interval are connected to the central limit theorem. And here's the answers that I was kind of looking for. Look, a confidence interval is a range of numbers. Yeah, a point estimate is just that. It's a single number. You obtain a point estimate by reaching into a population that has, let's just talk about means, it has some mean. You reach into that population, you grab yourself a sample of size n, you find the mean of that sample, and you go, gosh, that's all I know about the population. I'm going to say that mean is close to the population mean. Well, that's very much like playing darts, right? I got a dart, I'm going to throw a dart at the dartboard. I let the dart go. Before it hits the board, I cover up my eyes. I have no idea if it hits the board or not, let alone hitting the target. Right? So that's the thing about point estimates. Yeah, you can throw them up there, but you have no idea how accurate they might be. That's very different from moving up close enough to the board where you are 95% confident that you can hit the board, not the target, you can hit the board. Okay, now exactly where that dart hits within the board, I don't know. The target is inside there. All you're guaranteeing is you're going to hit the board. But that says if I'm 95% confident I'm going to hit the board, and the board is every point within the board is within this distance of the target, well, then you've got yourself some assessment, some estimate of the population parameter, population mean, and some estimate of your confidence with regard to getting close to it. That's the difference between the two. It's really the difference between the two. Now, what does the central limit theorem have to do with that? Very good question. Again, remember, reaching in, getting a sample, taking the mean of that sample, doing some machinations to put a bound on that mean. Ask yourself this. What is it that connects that little interval you've created to that population? Here's all the numbers in the population. Here's the mean. What's keeping your little interval from being over here, or over here, or over there, or over there? What is it that connects that interval to that mean? Well, it's the central limit theorem, because the central limit theorem says if you've taken a sample of sufficient size, then the sampling distribution, let's talk about that in a second, the mean of the sampling distribution is very close to the mean of the population. Okay, that's what connects this interval that you created out of data from the sampling distribution to the population. That, without the central limit connection there, you're just making up little intervals, and you're throwing them up at the population without any knowledge of it. It's like now you're throwing a lot of darts, and with no knowledge of exactly where they're hitting. So the central limit is the thread that holds everything together. So that's kind of what I wanted you to get out of that. I'm not sure I saw that in many of the responses, or maybe I just couldn't understand what you were writing. I don't know. So going forward, we've got hypothesis tests, and I got to tell you, most students have more trouble with hypothesis testing than they do with the confidence interval. And it's because it's so very easy to get lost in the weeds of hypothesis testing, because there's a lot of weeds. You're in chapter 9, 10, 11, 12, 13, you got 5 more chapters. You're going to be doing hypothesis tests of different flavors in all 5 of those chapters, okay? Every chapter is going to introduce new tests. You're going to just go to, I don't have my calculator with me, you're going to find yourself going to stats test and just going down this list of, I think I said there was 18 different tests coming up over the next 5 chapters. I think there's 14 actually. You know, each one's got some a whole lore and an information base associated with each one. That's the weeds. What I hope is that you can get out of the weeds and see that in general what hypothesis testing is. And let me tell you, hypothesis testing takes 2 things, generally 2 numbers. Generally a population parameter and a sample statistic. Perhaps it's 2 sample statistics. Perhaps it's 2 completely different things. But they have an apparent difference when you're holding them in your hand, 1.2, 1.4. What you're asking in a hypothesis test, is that difference significant? Or is that difference just due to sampling error, statistical variations? Or is it a real difference? Right? We've seen that any number of times. Is that different? Sure appears to be different. 1.4 is different than 1.2, but is it? Well, and the way that you do the test is the following. In all cases, you're going to make what is called a null hypothesis. And that null hypothesis is that, you know what, I don't think these are different. They're the same. Okay? That null hypothesis for different tests is going to show up with a slightly different format, but effectively, it always says these 2 numbers are the same. I'm going to make that assumption. Now under that assumption, you're going to do an experiment. If the results of the experiment come out consistent with that reduction, you're going to just say, see, I told you so. But if the results of that experiment come out somehow way out in the tail of a distribution, very odd, you've made an assumption, you get an odd result based on that assumption, then you're going to say, by what you're going to find in this chapter is called the rare event rule. You're going to say, I got a result that is highly improbable underneath this assumption. The result's right. Maybe my assumption's wrong. And that's the gist of hypothesis testing, no matter what flavor, no matter what type of test you're taking on. Okay, so keep doing what you're doing. I'll be back with you in a week. Again, if anyone has got specific assignments they'd like to have reopened for a few days to submit them and pick up some more points, let me know, and I'll get those open for you. All right, very good. Good luck to you going forward.